Okay, so now we're going to work on an example of generating handwritten digits using a generative adversarial network. So what the result is going to be is we're going to generate images that are handwritten digits between 0 and 9 that look super realistic but are actually generated by our neural network. So we're going to use a data set, a famous data set that has 60,000 handwritten digits that look like this, and our model is going to create brand new ones. So first thing we're going to do is we're going to import our libraries. We're going to use Keras for this. Keras is an abstraction of TensorFlow, and the good thing about Keras is it allows us to think about the algorithm and what's happening in our models rather than getting bogged down into the minutiae of implementing neural networks. So the next thing we're going to do is we're going to load the data set, which Keras has already set up for us, and we're going to just do some exploratory stuff and have a look at our data set. So as you can see here, we printed out a 5x5 grid of just a random set of data from our data set, and so these are what the images are supposed to look like. So these are the real ones that are really in the data set, and our model is going to create ones that look just like this. Next thing we're going to do is we're going to define our discriminator model. Now, a discriminator model is the binary classifier that is going to decide whether an image that it receives is real or fake. So it's a very simple model. We only have a few hidden layers here, and basically what we take in is an image. So an image that comes from either the real data set or it comes from the fake generated data from our generator neural network. So it's going to take in either one of those images and it's going to output the probability that this image, a given image, is either real or fake. So it's going to be like a vector of two values, which is going to provide us an understanding of whether it's real or fake. So we use a binary cross-entropy loss function, and that function will then allow us to gauge how successful our discriminator was at telling the difference between real and fake data. And then what we are going to do is we're going to update the weights and continuously improve our discriminator model, and it's going to get better and better at telling the difference between real and fake data. The next thing we want to do is we're going to define the generator model. So the generator model is going to define, it's going to generate fake data from a latent space. Now the latent space is just a random vector of noise. It's a random vector of random values. And those random values will feed into the network as an input, and what it will generate is like a fake image of a digit. So it'll be a 28 by 28 pixel image of a digit. And that image will be completely fake. It will not be something that is from the data set. So this is a little bit more complicated. There are some small things that I've learned about these networks, the generator network in particular, that I've added here. For example, there's just a few hidden layers. There's not many hidden layers, which keeps things really simple. But we add in batch normalization. Normalization allows us to have a little bit more stability in our network, as generative adversarial networks can be a little bit unstable if the conditions are not quite right. Batch normalization seems to help things converge a little bit faster and be a little bit more predictable in the results that we get. So that's why we have that. And this network is going to output an image of the size image shape, so a 28 by 28 pixel image. And so that's basically how it works. It's not too complicated. But I guess coming back to this just quickly is like the interesting thing to understand about these type of networks is that this is a cutting edge field of technology. This is a cutting edge field where every 6 months or even every few months, there's a new academic research paper that's building on top of the established knowledge. So the pace of growth and understanding is just really, really rapid, because this type of architecture was only really developed from about 2014. That was the first paper that came out that spoke about generative adversarial networks. And so it's been a really fast and rapid developing area. And why that's important is because at the moment, what you're seeing on the screen here is like a really basic neural network, but more recent papers from academic institutions have definitely improved on this and found ways to be more accurate quicker, work on different types of data with more accuracy. There's always something new and improved coming out in this area. And that's one of the benefits or interesting things about working in such a cutting edge space. But it's also one of the challenges because you have to keep up with those. But a network like this will work really, really well. And you'll see that in a second. So what we want to do then, we have our two models. We want to combine those into the network. So we want to stack them on top of each other, and what's going to happen is the generator is going to feed the data straight into the discriminator, and we're going to train those. But we have to be a little bit careful because we don't want the discriminator and the generator to be training at the same time. We actually want one to train and then another one to train, because if we train them at the same time, the weights are going to be constantly updating at such a rapid pace that it's going to be like a moving target. So the generator will generate an image, but that will already be wrong because the discriminator's weights will have already updated, and they're kind of moving away from each other in some way. So what we need to do is we need to freeze the discriminator's weights, so make it not trainable to start with. And when we want to train it, we'll unfreeze it and we'll freeze it back again, so that the generator can train without the weights of the discriminator being updated. So as you can see here on the screen, so we have the generator will generate an image from an inputs based on the latent space. Now the latent space, as we said, is a random vector of values, and that ends up, over time, that latent space ends up being like a compressed model of the features of our data set. So it actually ends up being like a model. And those data points feed into the generator, and the generator will create new data from that. Then the generator's image will come out as the output, and that will be fed into the discriminator. So the discriminator will get the image, it will provide the output, and the output is the probability of whether this is a real or fake image. And then we compile that all together and we make one big network that is actually two networks put together. Okay, and then next, what we want to do next is we want to just compile this all. We establish the size of our latent space, which could be any size. It could be 50, 100, 128, 500. Doesn't really matter. I just chose 128 because I'm a computer scientist, and that's what I think is a good number. So we generate our models, and as you can see here, we've got a summary of the models and how they're put together. It's really helpful just to understand like what kind of parameters there are, what the layers are, and all that kind of stuff at a high level. Then the last thing we need to do is we need to train the model and view the output. So we're almost there. So this is what we do. So firstly we need to scale our training data. So we need to actually do the same thing I think we might have talked about before, but basically our image data needs to have 3 dimensions. So it comes in 2 dimensions. It's a 28 by 28 pixel image, and actually needs to have a 3rd dimension, which is the grayscale dimension. So that's the level of grayscale that we have, because these are grayscale images that we're working with. And then from there, we want to loop through all of our epochs, and we want to do 2 things. We have a 2-step process. Firstly, we train the discriminator. So the discriminator, we take a batch size of real images, we take a batch size of generated fake images, we combine them together, and we give that to the discriminator. And the discriminator goes through and it decides for each of these images what the probability of them being real and fake is. And then through the loss function of that discriminator, we will get an understanding of how well the network is performing, and the weights will update based on the loss function using backpropagation and gradient descent, as is with a normal neural network. So the end of that, what we'll have is the discriminator weights will update, and it will get better at determining the difference between a real and fake image. Then the second step is we need to make sure that the discriminator is now frozen, not trainable, and we then need to train the generator. So training the generator is just a case of running the whole generative adversarial network. So we generate an image, we feed that through, the weights of the discriminator don't change, but we get the loss function for the generator at the end of that, because it's the loss function for the whole combined generative neural network. and it tries to understand, like, okay, it's only fooled the network half of the time or however much it's done, but it uses the loss function to update the weights in the generator network to provide better and better generated images. And the beauty of this whole model, the really interesting thing, I guess, about this whole model is that what will happen is the discriminator is constantly getting better and better at telling difference between real and fake. And because we're training them one after another, the generator is getting better and better at working out at generating really realistic images. And so they end up both getting really, really good because they're playing off each other in an adversarial kind of way. And so that's much better than just training one of them to get better. The last thing we do is we print out the loss, we save images periodically to see how the model is doing, and we plot the loss. So we'll have a look at that in a sec. But then when we run the network, you see here we get the loss for the discriminator and the generator. And this one, I think I might have trained at about 10,000. Yeah, trained about 10,000 epochs. And you can see here, so this is the plot of the loss. So you can see here, like it starts off really poorly, and then it kind of converges both in the middle here. And this is really good. Like this doesn't mean that the network has plateaued. What this actually means is that they're both getting better at the same rate. So in particular, you want to look at the discriminator loss, because I think that's the most interesting to me anyway, and that is just above 50%. So what you want to do is get kind of as close as you can to 50%, 0.5, and that's because you want the discriminator to be almost unable to tell the difference. Almost like a toss-up whether it's real or fake. It doesn't actually know. And that's how good the generator has become. Okay, last thing we're going to do is we're just going to look at some of these generated images. So as you can see here on epoch number 0, you can see here it's just garbage, just white noise. So this is coming from the latent space. It's just really rubbish. And then as we get to, say, epoch number 10,000, like we've got here, you can see here we've got some real looking digits. So there's a 6 here, I can see a 4 here, and I can see an 8 and a 9, a 2, a 7, a 2. So these are actually looking really real. And 10,000 epochs is not really enough. You could train this for 30,000 or 50,000. I think that would provide even better results. So yeah, so that's it. So that's an explanation of how the code works. Please give it a run yourself, and let me know if you have any questions.